Well, hello everyone. Good to see you today. My name is Anatole, and as you said, I'm a software engineer at Datadog, which you may have heard of if you're here, I suppose. And there I work on building the metrics product. And today I'd like to talk to you about the scaling challenges that we had with one of our larger production apps, which includes what we were seeing, how we got to the root of the issue, and the lessons that we learned in the process. So let's dive in. So imagine that it's Monday morning, the weather is nice, the sun is shining, you're having your coffee, you're doing well, you feel like the week is going to be productive. You see that pull request that has been open for a while, approved and ready to be merged. Change set is small, you feel confident. Good to go. You merge the PR, you hit the deploy button, take another sip of your coffee, sit back and relax, and then you get paged. Your coffee spills, your focus is gone, Monday morning ruined. And now you look into it and you realize it has nothing to do with your deploy. Page resolves itself, you get yourself another coffee, this time you put a lid on it. Another day, another PR, another deploy, another disaster, you get paged again, another coffee spill. And this is the story that was consistently happening for one of our apps. Every single deploy would page us. Now, obviously, we were annoyed. So we took a closer look. Why are we getting paged on deploys? What is going on? And one graph catches our eye. Our app's network latency is through the roof during deploys. Within a given data center, we'd expect a round-trip time of up to 100 milliseconds. And as you can see here, during deploys, we're closer to 1 second, so roughly 10 times what we would expect. And because of that high latency, our app cannot process data fast enough and falls behind, and we get paged. So the high-level ID makes sense. Slow networks means we get paged. But we set out to understand what's really going on during our app's restart, which would explain the high round-trip time. Why are the requests slow? Now, I'm going to have to give a little background on our app to continue. And you can view it as a very simple black box, which first consumes inputs from a stream, does some processing work with those inputs, and then produces outputs to another stream. Very simple model. It just processes an infinite data stream. All right. Now, alongside our app, we have a key value store. And in our case, it's simply a group of Redis instances. And when our app starts, it has to fetch a large number of keys from the key value store. And to do so, it uses the network, as the key value store is running on different machines than the app itself. Okay. Now, the key value store is the dependent service we were referring to earlier. This is where we are seeing a high round-trip time. And when our app starts, the GET requests to the key value store take a lot longer to complete. And these slower network requests mean that the time it takes to process each message from the input stream increases, so the app gets slower at processing the stream. And if messages arrive faster than the app actually processes them, we fall behind, and the backlog starts mounting. That's when we get paged. But this is only a high-level observation. Now we need to understand which part exactly is slowing down those requests. Why do we have a high round-trip time? At this point, our immediate thought is, when our app restarts, it makes a lot more requests than in steady state. See the spike here of requests at the restart. So maybe the key value store is struggling to process this surge of requests. Maybe the key value store is slow, and we should give it more resources to be able to handle that amount of requests. So we scale out the key value store to try it out. Adding more instances, increasing the CPU allowance, literally throwing money at the problem, and checking if we still have the issue. And we look at the results, and it's not so great. No improvement, still getting paged, same 1 second round-trip time, more coffee spills. Not great. Now, out of curiosity, we also take a look at Redis, our key value store's CPU usage after the scale-up. And we see that each Redis process uses less than 0.1 core. So whereas it could use up to an entire core. So it has plenty of CPU available, and it's not using it. And if we look at the request rate per key value storing process, again, on the Redis side, we see very low numbers as well. Each Redis process is serving around 5K requests per second, which is not a lot. And our benchmarks show that Redis should be able to serve roughly 10 times that amount of requests without a hitch. Okay, so clearly the key value store is not the limiting factor, and we decide to scale back down. It's not that simple. We're going to need to investigate deeper. All right. Now our focus switches to a small but relevant detail on the network path between the app and the key value store. We actually run a small network proxy alongside our app through which all requests go through. Here it is, layer 7 proxy is actually Envoy as the gateway for all requests to the key value store. And at this point, someone on the team wondered, could that proxy be the limiting factor? Could it be limiting our throughput to the key value store? Could be. So we think, let's look into it. Among other metrics, we look at the proxy CPU usage. And at that point, the issue becomes pretty obvious. When our app restarts, it makes all those key value store requests for our proxy, and our proxy completely maxes out its CPU allowance. It's a layer 7 proxy, so it has to reach each network packet entirely. So it has to make sense of the network layers, the TCP layer, and the Redis protocol layers. So read everything and make sense of the Redis level payload. Then take the Redis layer out of the packet, do some batching, assemble it with other Redis payloads from other requests, and craft a new payload. And with that new Redis payload, proxy needs to create entirely new packets from scratch, go through all the layers in reverse, the TCP layer and the network layers. Effectively, it's a lot of CPU work. And there's a lot to do, lots of bytes to read and write. And the CPU usage of the proxy scales linearly with the number of requests coming from the app. The more requests there are, the more CPU the proxy will need to process them. Very simple model. So if there is too low a cap on CPU, it will also limit the number of requests that can be processed. At this point, you might wonder what happens exactly if the CPU is overused. What is the exact mechanism here? Well, if the proxy falls behind on processing, the various network buffers will fill up, and eventually incoming packets will be dropped. They are dropped here, in the path from the app to the proxy, and they're also dropped here on the way back from the key value store. And we are actually seeing those dropped packets in network performance monitoring when looking at TCP retransmits graph. So the TCP mechanism will make sure that the segments are retransmitted if the sender does not receive an acknowledgement in time. So the more packets dropped, the more TCP retransmits we will see on that graph. And we did see quite a lot. So there was indeed a lot of packet dropped. And that's a very neat part of the TCP protocol. So in our case, the app in the key value store will slow down and calmly retry sending those segments later. They will retry here on the app side, and they will try here on the key value store side on the answer from the request. And eventually, they will all succeed in sending the segment. But this resistance in the flow of packets, this back pressure, by design, tells everyone to slow down. So from the app's perspective, the time it takes to do a round trip to the key value store has just exploded. Because a typical round trip request will have involved several retried set of TCP segments at different layers. Now this graph is to give a quick idea of the challenge our proxy Envoy is facing. A node receives in the order of 200,000 packets per second, not unheard of, but also a very much non-trivial amount. It's a lot of traffic, and that level of traffic typically requires tweaking configs to make sure everything will work properly. Now the obvious fix here is to increase the CPU allowance, up to however high it needs to be for the proxy to not max out that CPU allowance anymore. So increase the allowance, and that's what we do. And we're happy we finally found a solution. Let's ship and celebrate. That did not happen. Instead, we look at the results, and they're actually not as great as we were hoping. Round trip time did improve. Instead of plateauing at 1 second, it now oscillates between 0.3 seconds and 1 second. So we're in a better situation, but the problem is not solved. There must be another bottleneck somewhere else. So proxy, no longer the bottleneck. Let's look elsewhere. Now, to make this diagram a little clearer, I'm going to remove the inputs and outputs because it's irrelevant from now on. That's better. And one thing we haven't mentioned so far is that both the app and the proxy are actually co-located on a single host. They're interacting with each other over localhost. Now, one might wonder, how exactly does the host communicate with the key value store? Well, it uses a network interface provided by AWS called the Elastic Network Adapter. And at this point, someone on our team wonders, could we be reaching the limits of that interface? In other words, are we exceeding the AWS networking allowance? Now, thankfully, AWS provides a metric indicating whether the network card is dropping packets because of exceeded allowance. So we'll look at those metrics. This is the number of packets dropped at the AWS network adapter layer. As you can see, it's completely flat. So AWS is not dropping anything, but packets are still getting dropped. So our team starts to think for a while. We're bummed. What is going on? Where are the packets getting dropped? And after looking at many graphs and querying a number of metrics, a member of our team makes an interesting observation. The AWS network interface has 8 outgoing queues. It's where the kernel writes the packets that are then going to be flushed and read by AWS hypervisor. But our cloud instances are almost exclusively using TXQ0, while the 7 other queues sit idle most of the time. And this is a terrible use of your resources, obviously. Effectively, one queue is overused, while the others are idle. And this totally explains why we are unable to saturate the AWS network adapter. The bottleneck is simply earlier in the process. The bottleneck is here, between the proxy and the network adapter. We only have one queue. We need 8. Communications with the network card are simply severely limited. And so this is really at the interface between the software and the virtual hardware. And this part is actually handled by the Linux kernel. So a member of our team files an upstream bug report explaining that our machines are simply unable to make full use of their network interfaces, as only one TXQ gets used. And the consequence is that the throughput is logically very limited. And this gets attention from Linux contributor Daniel Borkman, who starts a discussion with other kernel maintainers and kindly provides an upstream fix in the Linux kernel. And as you can see, it's just a one-night diff, but with a very consequential outcome for many people and probably many companies. Thank you, Daniel. Now let's look at the results. So this is what we had, oscillations between 0.3 seconds and 1 second. And now, much better. The round trip is now consistently below 0.5 seconds. We've never had that before. But there's still something. We can still see an increased round trip time during deploys. So there must be some bottleneck that remains. So interface between Linux kernel and the cloud provider fixed. And at this point, we feel encouraged by the results we've had so far. There is improvement. But we're also a bit frustrated that after dozens of hours of engineering work, debugging was going on, and applying patches, we're still getting paged during deploys. It's frustrating. Now, we decided to take another look at the AWS network adapter metric, the NA metrics. Maybe we're actually saturating it now that we have full use of the 8 TXQs. Oof. Well, this is the graph of packets dropped by the AWS interface. And as you can see, it is dropping a good amount. So this means the kernel fix actually allowed us to increase our throughput up to saturating the instance limits. So very, very interesting graph and very useful metric to check in these cases. Now, let's look at the limits officially advertised by AWS. So AWS has several tiers of instances. For most instance types, they have what they call a network optimized flavor. which effectively means that for a slightly higher cost, you get an instance with much more network bandwidth. In this table, I took a random instance type, M5 16x large, and compared it with its network optimized equivalent. Roughly 10% more expensive, but 3 times as much bandwidth. And our obvious next move to fix our spurious pager alerts is, well, to start using the network optimized flavor. And those are the results. Packet drops at the AWS hypervisor level. Used to be a lot, and now down to 0. So it's very clear that the switching to the network optimized flavor had an impact. AWS is no longer dropping packets that are going in and out of the instance. Must be good for us. So let's see what the app sees now. We used to be around 0.3 to 0.5 seconds during deploy, and now deploy are basically invisible. We're not saturating any layer anymore. We're good. And this time we can really celebrate. Now, what can we learn from this? It was a long and protracted investigation with many steps, frustration, hope, good surprises, bad surprises. Possibly the first realization is that we ran on a pyramid and we need each layer to work. As software developers working on the app layer, we don't have the guarantee that everything underneath works perfectly. And sometimes we have to dive deep to understand issues that are below the app layer. This is not perfect, the app layer is not perfect, but also the platform layer is not perfect, and neither is the infrastructure layer. And unusual scale often brings unusual bugs, especially in the networking space where there are complex interactions between the different layers. So we must assume that each layer is a work in progress with its strengths, but also with its bugs. Now, each layer is very specific, and so we have different teams specializing in different layers. The app team is responsible for fixing the app layer, while the infra team is responsible for fixing the infrastructure layer. And because there is such a complex set of interactions between the different layers, we need the different teams to talk together. They have a different set of skills and complementary knowledge. And the developers are generally not expected to know what TXQs are or why they exist. And we also need the open source community with whom we also want to keep a discussion going. We mentioned earlier that the Linux kernel fix was essential in solving this problem. So really it takes multiple teams to solve a complex problem like this. And it requires that one group advertises the problem and asks for input for other groups of people. Now the final realization is that just like one trade may hide another at the crossing, and one trade being out of the way does not mean that the path is clear, well, one bottleneck may hide another. And we can't just assume that fixing one bottleneck will make the entire problem go away. We first saw that we were not exceeding the AWS bandwidth allowance, but once the kernel patch was applied, we ended up saturating the AWS network adapter and exceeding that allowance. So after making changes, we can't just rely on previous conclusions. We have to go back and check again. One bottleneck may hide another. With all that said, I hope you enjoyed this talk. Thank you very much for coming, and I'll be staying around for a bit in case there are any questions. Thank you.
Thanks, Anatole. We can take questions in the aisle. We can also just come up and chat with Anatole since we have the rest of the evening. Thank you all so much.
Question?
Yes.
Did you have all those metrics created while you were debugging the bottleneck, or did you have to create some to identify the bottleneck?
I believe most of them we already had, but for example, Envoy, the Envoy proxy comes with a lot of bundled metrics, but it generally, they have so many that you really need to know what you're looking for. So generally, the breadcrumbs were buried, but they existed. I think there was just the ANA metrics, the AWS Network Adapter metrics, which we had to manually enable to come up with conclusions. And then there are the TXQ observation, which we only could have in CLI, and for which, to my knowledge, there is no metric currently being collected.
Okay. Thank you.
Thank you. Sorry, yes, yes. I don't really remember exactly the process, but yes, I think it's not typically what people get out of the box. It is very, I mean, I would now enable it on everything I have, yeah. Yes? We started having the problem in September of last year, and we really dug deeper from December to February. So it was like 2 months of real investigation with a bit longer of actual just feeling the pain of the page. Yes, it took a while mostly because there was a lot of back and forth between different people and different teams. And at several points in the investigation, there was no clear path forward, like what should be the next thing we check, what is really going on. Like we really had to wait to think about the problem and think of new ideas and talk to various people. And we did also, like I didn't mention everything, but we did also try a few other things that didn't pan out, that like we suspected at some point that we had another type of misconfiguration on our host, and it turns out we did not. Yeah. So roughly 2 months, yeah.
Hi.
Hi.
After you did the fix, like you had a suggestion and you implemented the fix, did you have to wait for a new deployment, or did you initiated a fake deployment?
No, we would initiate a deployment that is for which the only purpose was to check if there was an improvement or not. Yeah. We're generally very excited to see the results, so we're like, even if it's a bit more work, we wanted to know right away. And again, because there were many things we tried that didn't pan out, we also wanted fast feedback on like, is this worth digging deeper, or should we branch out to another possible fix, if that makes sense.
I guess I'm interested more in the interaction between like the multiple teams involved. I guess my 2 questions are like, what do you think went well, and what do you think you would do differently if you had to do it again? Which you may well have to, so.
Yeah, that's an excellent question. I think what went well is that everybody I spoke to about the issues we're having were very we're making a good faith effort of like putting in the time to research. Can they help? Does it match a problem they know? So there was a lot of goodwill from everybody involved. Interestingly, I actually, so Laurent Bernay, who reported the bug upstream, I actually randomly met him at some point in the cafeteria to talk about this bug, and he was like, "Oh, maybe I have something that like he was starting to see this problem, and so it's actually through random interactions that I ended up talking to the right people. So it can be hard to reach out to the right people, especially in an organization that is somewhat large. So perhaps it could be easier to know who to talk to for what kind of problem, especially in large organizations, if that makes sense. Yes. No. No.
I just want to say another round of applause for Anatole. Thank you.
No. Thank you very much.